Okay, we're going to start with chemistry, and the first item that we have is atoms, ions, and molecules. So let's start with a chemical element. An element is the simplest form of matter. Matter occupies space and have unique properties. Okay, let's take a look at some of the elements that we have in our body. For example, oxygen, carbon, hydrogen, as well as some other examples of elements. So if we scroll down, we can see the atomic structure of the elements, and we can see that all the elements are going to have protons, neutrons, and electrons. Right here, you can see the nucleus with protons, neutrons, and flying around in energy levels, as you can see right here, or shells, they're going to be the electrons. The number of protons and neutrons in the nucleus is going to be the atomic mass. The number of protons only is going to be the atomic number. You can see this example right here, the nucleus and the electrons flying around. This is carbon. In the nucleus, we have protons 6, neutrons 6. Sometimes this number of neutrons changes to 7 neutrons, 8 neutrons, and in those cases, this carbon is going to have isotopes. Isotopes are the same element with different number of neutrons. This excess number of neutrons is going to be unstable. So what the carbon is going to do to try to become stable again is going to release radiation. And now these carbons with different numbers of neutrons are going to be called radioisotopes. It's going to be a radioisotope because it's going to release radiation. Physical half-lives, since they release radiation, that means that they decay. So the amount of time that takes for an isotope to decay 50% is called the physical half-life. The biological half-life is the amount of time that it takes for the radioisotope to decay 50% in the human body. If we scroll down, we're going to see ions, electrolytes, and free radicals. Ions are particles with an equal number of protons and neutrons. Right here, you have sodium and chlorine. The electrons are negative. Sodium is going to lose this electron and is going to give this electron to chlorine. Now, chlorine is going to have one more negative that came from here. So therefore, the chlorine is going to become more negative. Sodium lost this electron. Therefore, it becomes less negative or more positive because you're going to have more number of protons. When you become more positive, you're going to be called cation. And if you become more negative, you're called an anion, as you can see right here. So we have cation if has more positives, and it's going to be an anion if it has more negatives, in this case, the chlorine. Now, what is the force that is going to put together these two, that is going to make this possible? When this electron goes from sodium chlorine, these two are going to get together by a force called a bond. So when elements get together, they form bond. What is the bond? Is the energy necessary in order to put these elements together. So in the case of the sodium and chlorine, when you put them together, you're going to form sodium chloride, which is your regular table salt. So if we keep scrolling down, we're going to see right here electrolytes. What happens when you put sodium chloride in water? Sodium chloride, the salt, is going to separate, is going to ionize into an anion and a cation, which is the chlorine and the sodium. In that case, when they dissociate in water, they become electrolytes, and they have the ability to transfer electricity. That's why they are called electrolytes. And that's what you get, for example, when you drink Gatorade. Free radicals are particles that they're going to get an extra electron. And they are very bad in our body. They destroy many organic substances that we have in our body. Therefore, they need to be stopped, or they need to be changed into a more stable substance. And that's why we are going to use in our body antioxidants in order to achieve that particular purpose. Let's scroll down and we see molecules and chemical bonds. We already talked about one of them, which is the ionic bond, when I mentioned the example of the sodium chloride, your regular table salt. In addition to the ionic bond, you also have other bonds, which are going to be the covalent bond, hydrogen bond, and van der Waals forces. In the case of the covalent bond, you are going to have elements which they're going to share the same number of electrons. In this case, you have the hydrogen, it has one electron. The other hydrogen has one electron. So in order for this hydrogen to get 2 electrons, it needs to share this electron with this other hydrogen. So as you can see here, they both share, and now they have 2 electrons. Since they share, this is a covalent bond. Again, in covalent, they share. So you have in here carbon sharing 2 electrons, oxygen sharing 2 electrons. So that's why you see 4 in here and 4 in here. And this is going to be carbon dioxide. If we scroll down, we can see right here that covalent bonds can be polar or non-polar. Right here in nonpolar, the two elements are going to share, and the sharing is going to be, let's say, 50 and 50%. In the polar covalent bond, you see here they share, but the sharing is not equal. This one is so big compared to this other one right here that this big oxygen is going to attract the electrons that the hydrogen has towards this side, and because of that, it's going to form negative area and a positive area. In other words, negative pole and a positive pole, and that's why this is called polar covalent. Okay, the next item is hydrogen bond. Obviously, it goes without saying, I think, that in order for you to have a hydrogen bond, you have to have a substance that contains hydrogen. Let's talk about this. This is water. So how many molecules of water you have? 1, 2, 3. What forms water? A covalent bond. But in between, you see here this dotted line. This dotted line is showing you the hydrogen bond, which is formed in between two molecules of water, because the molecule of water itself is formed by the covalent bond. If we keep going down, we see here van der Waals forces. There are weak and brief attractions in between atoms, and it's necessary to, for example, form protein folding. Okay, the next item is water and mixtures. Water is very important in the human body. Almost 70% of the human body is water. Substances that are going to be able to dissolve in water are going to be called hydrophilic, as you can see here, and substances that don't dissolve in water are going to be called hydrophobic. Water has very important properties, such as being the universal solvent. Another properties that water has is going to be addition and cohesion. Addition is the tendency of substances to cling to one another. Like, for example, if you have a glass of water, addition would be the water trying to cling to the glass itself. It has a very important chemical reactivity, because a lot of chemical reactions happens due to the presence of water, and thermal stability as well, because you need a lot of energy in order to increase the temperature. Okay? And that's a very important example of why water is used as a coolant, for example, in engines, in the car, where you need a lot of temperature in order to raise the temperature of water. The next item is going to be solutions, colloids, and suspensions. Solution is composed of solute and solvents, where solutes can be sugar, salt, and a solvent most of the time is water. Why we need to talk about this? Because there's a very important solution in our body, which is going to be blood. Our blood is a suspension. As you know, the blood is a fluid. It's a red fluid. Why is it a fluid? Because it contains water. And why is red? Because it contains a whole bunch of red blood cells. It's called a suspension because the red blood cells are suspended in that water. When this suspension is put in a centrifuge, the centrifuge will spin and all the red blood cells will go to the bottom. Why? Because they were suspended in the water. Now, as you can see here, all the red blood cells at the bottom, you know water is crystal clear. Then how come this is not shown as crystal clear or translucent? Because in water, you're going to have other substances in your blood, such as, for example, proteins. These proteins, even though you are spinning the blood, the proteins will not fall to the bottom like the red blood cells. This water mixed with proteins is a colloid. Once the substances mix with water and they can be separated, it turns into a colloid. So a suspension is when they are mixed like this, but these red blood cells will go to the bottom. So in that case, they are suspended. But when they are mixed, but they cannot be separated anymore, then this becomes a colloid. Colloid suspensions, they all vary basically depending on the particle size. If we keep scrolling down, we're going to get to acid, bases, and pH. Okay, so what is pH? The pH is the number of hydrogens in a solution. As you can see here, derived from the molarity of hydrogen. So pH got to do with hydrogen. You can see right there, formula of pH. It says in here, pH is a negative log of concentration of hydrogens, and pH show you in there 7. Why? Because 7 is neutral, as you can see right here. So everything that goes from 0 to 7 is called acidic. Everything from 7 to 14 is called basic. So that means that these substances in here have more hydrogen. That's why you see here, you have lemon, right, which is very acidic. What happens if you put your fingers in acid, for example? You're going to get burned. What happens when you put substances that are very basic? You're going to get burned as well. In our case, what we need to know is the pH of blood is going to be 7.35 to 7.45, which is almost neutral. It's right here, right? It doesn't get to 8. So the number of hydrogens that is going to give you the pH is measured based on concentration. Now, how can this concentration be expressed? Well, it can be expressed in molarity, in percentage, weight per volume,